Hi folks, and welcome back to Physics with Captain Rod. I make this video here to help you learn how to write Newton's second law equations. So just a little reminder here, or a little bit of review. So I wrote it right here. Newton's second law says that the net force acting on a system is equal to its mass times the acceleration. And it's very important to realize that Newton's second law is a vector law. That's what these arrows are about here and here. Now, it's usually a two-step process here, and I kind of shorthanded this, but the first step is to typically draw a free body diagram. And I've got other videos on how to draw free bodies. That's not what this video is about. This video is going to be about step 2, how to use your free body to write Newton's second law equations. So, reading the directions here, assuming a generic acceleration, i.e., assuming all the examples, there could be an AX and an AY, meaning that these are all going to be kind of two-dimensional in nature, at least potentially could be two-dimensional in nature. We're going to write Newton's second law equations for each free body, assuming that the free bodies are complete. We're not going to add any other forces to them, and we're going to assume relative magnitudes from the vector lengths. So let's get started here. We got this first free body here. We got this object here with the two force vectors given. Now, my standard advice for this is to identify the acceleration direction, call that positive. So since force 1 is bigger than force 2, then we can infer from that that this object's going to accelerate to the left. So we're going to write out our Newton's second law equation, which says the sum, try this again, the sum of all forces acting on this object is equal to mass times acceleration, and we're going to call left positive. Now, this is just a one-dimensional problem, no reason to do subscripts. The reason for left positives, looking at the length of these vectors, this object is going to accelerate to the left. And the Newton's second law equation for this would be F1 minus F2. F2 would get the minus sign because F2 is to the right, and we're calling it left positive. And then equals MA. And there is our Newton's second law equation for this free body. Fairly simple example. Let's go ahead and move on here. I think I've got some more here. All right, here's an object. We've got a couple forces acting on this thing. 3 forces, I guess. Oops. There we go. All right, now this one is a two-dimensional problem. So what we're going to do, right, we're going to take Newton's second law, which is, remember, net force is equal to mass times acceleration. And remember what the net force is, right? When you add vectors, you do so by adding components. So we're going to do the x direction first, the sum of all forces, and we're going to add x components now, is equal to mass times acceleration in the x direction. So what we're doing here is we're applying Newton's second law. I should put a coordinate system in, x, y, and we are now applying Newton's second law in these directions. So now, when we look at this free body here, let's talk about force 1 here. Force 1 has a component to the right, adjacent to the angle theta, and a component upward here, opposite to theta. In fact, maybe I'm going to go back here and color code those components. Any other colors to choose from? I guess we'll use this green here. All right. So there is what I will call F1x component. Here's F1y component. While I'm at it, let's just do force vector 2 here. X component, y component. So that one is F2x. This one right here is F2y. So what I'm doing here is just breaking these force vectors into components. Right, now when we write our Newton's second law equation, and it's hard to tell for sure which way this thing's going to be accelerating, right or left. I'm just going to take a guess at it. We're going to do right positive. If these things are perfect, we'd be comparing the sum of these two vectors to this one. Looks like it'll probably end up to the right. But now, F1x is adjacent to theta, right? And this hypotenuse is what we're calling F1. So F1x is going to equal F1 cosine of the angle theta. plus because this vector points to the right. Right, now, let's talk about this one. The component of force 2 that is to the right is here. It's kind of hard to see, and I don't even remember what I called that angle anymore. I probably called it alpha. I'm going to assume alpha. I kind of covered it up there, but so this is the force component adjacent to this angle, and that's the one I probably had labeled as alpha. So force 2 cosine alpha. That's what we're going to call it now anyway. Now force 3 here points to the left, all of it, so minus force 3. And that's it. Now we've considered all forces in the x direction, so equals ma, and that acceleration, it would be in the x direction, x component of the acceleration. Next, we'll write a force equation for the y direction. Sum of all forces in the y direction equals mass times acceleration in the y direction. Let's go ahead and call up positive. Right? And we look at these three vectors. This one right here is the y component of F1, and it is opposite theta. So its magnitude would be F1 sine theta. This one right here is opposite the angle alpha, and it's down, so minus F2 sine alpha. This third vector here does not have a y component. If you want to put 0, that's fine. I'll just leave it blank. So equals mass times acceleration in the y direction. So what we've done here is we took the original free body. We broke this force down into its x and y components. We broke this force, whoops, right here, into its x and y components. And then we wrote Newton's second law equations for both the x and y directions. Now, you might be asking, could we just find the net force first and figure out what direction that is? Say maybe it's this way. And then set that equal to mass times acceleration. And the answer is yes. That would work fine as well. Written like this, what we would be getting is the acceleration components, but that would do the same thing as finding net force first and then writing the Newton's second law equation. I like to start it out like this because it's pretty common in physics, particularly two-dimensional problems, to write Newton's second law equations in two different directions. Let's see here, Mr. Duck. I got a great big duck at home, so now we're going to start working on drawing equations and writing the free bodies. I'm sorry, drawing the free bodies and then writing the equations from the free body. And we're going to start with this picture of Mr. Duck here. So when we think about the forces acting on that duck, I wonder if this will let me copy Mr. Duck here. No, not going to let me do that. All right. Well, we'll just go ahead and do this. Normally, generally speaking, my advice here is to always use a separate picture. Don't use your first picture for the free bodies. I would normally draw another picture of Mr. Duck and then draw the free body, but I'm going to go ahead and just draw the free body right on this picture. So Mr. Duck's got a significant weight, probably, so we can, we would draw that as a force vector down. Now we could call it the weight of the duck, or we could call it the gravitational force, or we could write how it's calculated, which is mg. Any one of these is perfectly acceptable. Also, where you put this force vector, up or down, does not matter. Forces have what's called a line of action. If you wanted to draw it, say, down here like so, that'd be perfectly fine too. All right, now, surface is in contact here. The duck's foot is in contact with the ground, both the feet. They are effectively pushing up on the duck. That's why the duck isn't accelerating downward. So we're going to go ahead and put an upward force. Again, this is on the duck. This is an example of what we call a normal force, because this force makes a right angle to that surface. And normal is just a kind of fancy word for perpendicular. And it's pretty well lit. Those are all the relevant forces acting on Mr. Duck there. Force equation's pretty easy. Sum of all forces equals ma. We're going to be applying this in the y direction. I'm just going to go ahead and put like up positive. and we look at our free body, and this normal is up. I'm going to go ahead and call it mg. The mg is down, and the duck is not accelerating, so we're going to put a 0 there for the acceleration of the duck. Pretty simple equation, pretty simple free body. Moving on. Oops. Oh, there we go. Working in words a little trickier. Ah, so now Mr. Duck is on an incline. So let's talk about how that changes the free body. And my short answer is it doesn't. Okay. Mr. Duck here, we still got the gravitational force vector down, mg. Surface in contact. So we're going to have a force vector there, and notice that the duck is not accelerating. That force vector does in fact point this way, because the net force on the duck, if he's not accelerating, and that was the intention here, I think I said that in the directions up above, the net force is 0. So I would argue that's a correct free body of the duck. However, you notice this angle here is no longer 90 degrees. It's very common to, when we deal with surfaces interactions like this, to draw the forces in component form. There's going to be a piece of that force which acts this way, normal to the surface, so we'll go ahead and call that a normal. And then there's going to be a force component parallel to the surface, like this. And when you talk about these force interactions, this one that makes a right angle is referred to as the normal, and this tangential force is what's called the frictional force. And hopefully you had some sort of idea about that, how this stuff works. You know, if this were a super icy incline, Mr. Duck couldn't sit there. There wouldn't be enough friction, and he would slide down the incline. Now, I'm going to read the directions here. Are we supposed to write Newton's second law equations? I believe the answer was yes, so we're now going to do that. Oops. If I can get this centered. Word is a little funny to work with. I like my other program better, but it's nice for scrolling. All right, now, there's some things to realize about these types of free bodies. When you're dealing with vectors, you got to work with coordinates. If we used our standard x, y coordinate system, the frictional force and the normal force will have to be broken into components. So, whoops, not what I wanted to do there. What we're going to do is we're going to work in a set of coordinates that look like this. All right. Just put a coordinate system over here. X, Y. And by doing it this way, the frictional force is parallel to the x-axis. No components needed. The normal is parallel to the y-axis. No components needed. Only the gravitational force needs to be broken into components. Now, that comes with a little bit of geometric work here that I'm going to chat about. If I were to draw, I'm going to put a couple lines here. Here's just a vertical, or a line like this, parallel to the normal. And I'm going to draw a vertical line right here as well. If you look at this triangle right here, 15 degrees is the small guy. That makes this one 75, and that makes this one between the normal and the vertical 15. And that makes this one here between the mg and this dashed line 15 degrees. Let me get rid of some of this stuff here. Not sure how much I can get rid of. Oh, good, all of it. All right, so our gravitational force vector, we can do this. We can do a component this way, a component this way, and this would be a 15-degree angle. And that makes this vector equal to mg sine of 15 degrees, and it makes this one equal to mg times cosine of 15 degrees. I'm going to do lots more videos on drawing free bodies of things that are on inclines like this, so if you're having trouble following the geometry of that, it's all right. Many more examples. Okay, so now we can start writing our force equations. Sum of all forces in the x direction equal to 0. I'm going to go ahead and call up and right the positive x direction. And when we look at our free body now, that's this one and this one. That one didn't get drawn perfectly parallel, but that one was supposed to be perfectly parallel to the x direction. So we're going to have plus the frictional force minus mg sine of 15 degrees equals 0. And again, what we're doing is we're adding force components in that direction. So that's this one up and right, this one down and left, and they add to 0 because Mr. Duck is not accelerating. All right, next equation, the sum of all forces in the y direction also equal to 0. Mr. Duck is not accelerating. We're going to call kind of like up and left the positive y direction. The normal is in that direction. And this component right here, the mg cosine 15, also in that direction. So we're going to have plus n and then minus mg cosine of 15 degrees, and that's pretty well it, equals 0. So again, there's an example of drawing a free body diagram for a two-dimensional problem and writing the Newton's second law equations for it. Let's see if I got another example in my handout here. Draw free bodies and write the Newton's second law equations for the following system. Timmy, the Rex-Timmy system. Let's see, Timmy, the Rex, Timmy system. Okay, so I'm going to take a moment here and change programs here because I think this one's going to be important enough. That word is not a great one for what I want to do here. Hopefully the and actually looking at the video, 16 minutes. I think what I'm going to do is just stop this video and make this a 2-video series for this. So I'll make the next one. I'm going to use my other drawing program for that free body. I think it'll serve us a little bit better. So end this video right here. Hopefully you're going to watch part 2 of this where we draw free bodies of Timmy here and Mr. Rex. See you in a few minutes, hopefully.